Hello students, and welcome to the lecture of colligative properties of a non-electrolyte solutions. Colligative properties by definition are affected by the number of solute particles in the solution but not the identity. So those are properties that will be affected by how many particles of solute are there, but we really don't care about what kind of solute it is. It is molecular, polar, non-polar, that doesn't matter. What matters is how many of them are there. It has to work though relatively when we have a diluted solution, so it works perfectly when we have less than 0.2 molar of a solution. The first property we will look at is vapor pressure depression. So since we said those colligative properties depend on number of solutes, then what does that mean to you? It means that the more solute, because the lower the pressure. That's why we call the property vapor pressure depression. So the lower the pressure is, it's because you have more particles. So more solute, more depression in the pressure. So vapor pressure of the solution will be always less than a vapor pressure of a pure solvent. If the solute is non-volatile and there is no really measurable vapor pressure, it's when we really apply this. And the more solute, the larger depression on the vapor pressure. So the best way to look at this and understand it is to see the following picture here. When you have a pure solvent, you have a lot of water, like particles or molecules, if you wish, on the surface that can escape and cause vapor pressure, right? So this is what happens when you have a pure solvent. However, that surface right now, when you have solute dissolved in it, and that solute is not volatile, right? There are less blue molecule on the surface than it is in water. So less of them will escape, and therefore the vapor pressure will be lower. The more solute you have in the solution, the surface will even have less water molecules to escape, and therefore the vapor pressure will be lower and lower. So more solute, more depression in the vapor pressure. So the way we're gonna calculate that by using Raul's law, P1 is the vapor pressure of the solution, which will equal to the mole fraction of the solvent times the vapor pressure of the pure solvent before I added anything to it. In any solution, the mole fraction of a solute plus the mole fraction of the solvent should equal 1. And that's, of course, assuming we are having one solute in the solution. So therefore, you can also calculate the mole fraction of the solvent by subtracting the mole fraction of the solute from 1. The difference in the vapor pressure, which is how much depression is going to happen, which will be the vapor pressure of a pure solvent minus the new vapor pressure. That's the difference. That the difference came as a contribution of the mole fraction of the solute times the original vapor pressure of a pure solvent. Here is an example. Calculate the vapor pressure of a solution made by dissolving 82.4 grams of urea, the molar mass of urea given as 60.06 gram per mole, in 212 milliliter of water at 35 degrees Celsius. What is the change in vapor pressure? The vapor pressure of the water at 35 degrees Celsius by its own is 42.18 millimeter mercury. So I should immediately know that it is a solution. It's a colligative property question. And what they are asking about is vapor pressure depression. So I immediately put the equation down. Pressure of solution equals mole fraction of solvent times pressure of a pure solvent. Okay, So let's see what we have. Did we have the pressure of a pure solvent at this temperature? Yes, they have given me that. Can I calculate the mole fraction of water in this case? Yes. Why? Well, first, can I calculate moles of urea? And the answer is yes. I have 82.4 grams of urea, and I'm going to convert that into moles of urea, and that will be, there are 1 mole of urea will have 60.06 grams of urea, and that is going to give me, if I do the math here, 82.4 divided by 60.06, that will be 1.37 moles of urea. Now, what is the mole? How many moles of water do I have here? I have 212 milliliter of water. I'm going to convert that into mass using the density of water. And then I'm going to convert that into moles. 1 mole of water has a molar mass of 18.02 grams of water. And when I do the math, 212 divided by 18.02, that will be 11.8 moles of water. So now I am ready to calculate the mole fraction of water. The mole fraction of water is moles of water over the total moles. So that will be 18.8 divided by 18.8 plus 1.37. So when I do this math, the answer will be 0.893. Now you are ready to do your calculation. So the new pressure of the solution will equal 0.893 times 42.18 millimeter mercury, and that will equal to 37.6 millimeter mercury. So of course the solution has lower vapor pressure than a pure water. If you are to calculate the difference here, or what is the change in vapor pressure, then that will be 42.18 minus 37.6, and the answer will be 4.6 millimeter mercury. Let me write it here. 4.6 millimeter mercury. Okay, let's move on to the next slide. The next colligative property is called boiling point elevation. So now this is different. It means more particles, more elevation in the boiling point. So that has to do with the vapor pressure, because the lower the vapor pressure, the more you need to heat the solution so that the vapor pressure will equal to the outside pressure for the solution to boil. So more solution, greater increase in boiling point. Look at this diagram. You will see how the boiling point of 1 molar sodium chloride, how it's much higher than just the boiling point of pure water. Now in this diagram you also can see how there is the dash is the solution and the solid line is a pure liquid, and you see how the boiling point of the solution is higher than the boiling point of pure water. Mathematically, the change in the boiling point, which is the boiling point of the solution minus the boiling point of a pure solvent, the change has to be a positive value. That's why I subtract the pure solvent from the solution, because the solution is a higher value and I need that difference to be positive. And the equation that you need to know and we will use is the change in the boiling point will equal a constant the boiling point constant, times molality of the solution. Pay attention, we are going to use molality here for our calculation. Okay, that constant, Kb constant, which is degrees Celsius per mole, that's a constant that belongs to the solvent, that it's a property of the solvent. Every solvent has its own Kb value. The next colligative property I'm looking at is called the freezing point depression, and in this case it's total opposite. The more particles you have in your solution, the more the depression is in the freezing point, the lower the freezing point. Now, freezing is causing disorder, right? Freezing, and then when you have to put it into more order, when you want to put it down, you're going to have to remove energy. And the solution is more disordered, so you need to remove more energy, freeze at lower temperature, and that's why the freezing point gets to be lower and lower. Okay, so now if you look at this diagram again, which is the phase diagram, and you focus now on the freezing point, you will see how the dash, which is the solution, has a lower freezing point than the water, which is the solid line. That difference is what I call delta TF, and it's calculated as the freezing point of a pure solvent minus the freezing point of a solution. Again, this time I chose that because, again, I need that change to always be positive, and because I want it to be positive, it is solvent minus solution, because the solvent has a higher freezing point than the solution. Delta TF equals Kf times molality again. So it's very similar to the boiling point equation. M is molality, Kf is the constant that belongs to the solvent, and here is a table that shows you different Kb values and different Kf values. So what does it mean? I want to just make you understand how to read those. The normal boiling point for water is 100 degrees Celsius. What does Kb of 0.51 for water means? It means that you're going to have 0.51 degrees Celsius higher in boiling point for every mole of solution, right? It's degrees Celsius per mole. That's how you read the Kb and the Kf values. For the freezing point, it means for that you're going to have 1.86 degrees Celsius lower in the freezing point for every 1 mole of solution when it comes to water. Let's solve problems. What is the freezing point of a solution that contains 478 grams of ethylene glycol, which is the antifreeze, in 3,202 grams of water? The molar mass of ethylene glycol is given as 62.01 gram, and Kf for water equals 1.86 degrees Celsius per molar. It's a freezing point depression question. They gave me Kf, that's your hint, and they are talking solution. So the change of the freezing point equals Kf times molality. That's the first thing you need to write down. What they want is what is the freezing point of a solution? So they want the new freezing point. They gave me Kf, and I think I have what it takes to calculate molality. So delta Tf will equal, Kf is given as 1.86 degrees Celsius per mole times. Molality is moles of solute. Now, do I have grams of solute? Yes, which is 478 grams of ethylene glycol, and then they gave me the molar mass, so 1 mole of ethylene glycol has a molar mass of 62.01 grams of ethylene glycol. And then I do have the grams of water, which is the solvent. I'm just going to say in kilogram, it's 3.202 kilograms of water. Now I do the math, and let's do the math here. 1.86 times 478 divided by 62.01, and then I'm going to divide by 3.202, and that is 4, I need 3 sig fig, 0.47 degrees Celsius. That is the change. But what is the new freezing point of a solution? Remember, delta TF is equal TF of water minus TF of solution. Okay? So 4.47 will equal 0 minus the freezing point of the solution. Therefore, the new freezing point of the solution is negative 4.47 degrees Celsius, right? Because what I calculated is the change. And remember that property is called freezing point depression. Solution will have lower freezing point. Okay, another question. A solution of 0.85 grams of an organic compound in 100 grams of benzene has a freezing point of 5.16 degrees Celsius. Benzene normally freezes at 5.50 degrees Celsius. What is the molality of the solution and the molar mass of the organic compound? Kf of benzene is given as 5.12 degrees Celsius per molar. I'm going to start one more time by writing my equation and see what I have and what I need to calculate. They gave me Kf and they gave me delta TF because they gave me the freezing point of the solution and benzene, which is my pure solvent. So I'm going to say, okay, in this case, it will be 5.50 minus 5.16 degrees Celsius equals to Kf is given as 5.12 degrees Celsius per molar, and molality. I can calculate molality. So molality will equal to, let's do the math. And I will divide by 5.12. And molality in this case will be 0.066 molal. Okay? Now, what is the molality? We already calculated that. What is the molar mass of the organic compound? Okay, in this case, I need now molality is moles of solute over kilograms of solvent. Okay, now molality is 0.066 equals to, I can calculate moles of solute, and the kilogram here by molality is the definition is I have 1 in 100 grams of benzene, so I have 100 gram, and I'm going to convert that into kilograms, so that will be 0.1000 kilogram. Okay, now number of moles will be calculated as 0.066 times 0.1, and that will be 6.6 times 10 to the negative 3 moles. Now that I have moles of my compound, I'm going to put it up here to finish it so you guys can see it. I have 6.6 times 10 to the negative 3 moles, right? So now I need to calculate the molar mass, which is a gram per mole, right? So how do I calculate the molar mass? I have 0.85 grams divided by 6.6 times 10 to the negative 3 moles. It's a gram per mole. And the answer will be 151.5 gram per mole. All right, let's move on to the next slide. Colligative property, as we said, depends only on the numbers of solute particles and not the types. So the ones we already have looked at are the vapor pressure lowering, boiling point elevation, and freezing point depression. You do need to know the equations related to each one of them so you are capable of solving problems about them. All right, so now what is it? What happens if we have electrolytes? Electrolytes do dissociate into ions. So 0.1 molal sodium chloride will give me 0.1 molal sodium cation and 0.1 molal chloride anion. So I have a total of 0.2 molal ions. And since colligative properties depend on number of particles, I need to take that into account when I have electrolytes that dissociate into ions. So I have to find out what we call the Vienhof factor, which is actual number of particles for every number of formula units. So if I have a non-electrolyte, they don't dissociate. So for every formula unit, you have one particle, so I equals 1. However, for sodium chloride, every formula unit will give you 2 particles, so I equals 2. For calcium chloride, every formula unit will give you 3 particles, so I equals 3. Now, in this case, since I need to take into account number of particles when I address colligative properties, I need to find out and I need to incorporate it in all of my equations, specifically for boiling point elevation and freezing point depression, okay? So again, we will have another lecture in the next module that will also help you identify strong electrolytes and how they dissociate, and the I will be part of your calculation if you happen to have electrolytes. If you are not working with electrolytes, like sucrose in the table, for example, it's a non-electrolyte, I is equal 1 and it wouldn't matter. But for other electrolytes, it will matter. Now, there is a calculated one and a measured one, and since we cannot really figure out what will be different, the difference between them, so we are just going to assume the calculated ones in our class. Okay, so here is a problem in which we're going to apply this. Which solution would have the lowest freezing point? So the first thing I remind myself is, what is the freezing point as a colligative property? It's called freezing point depression. More particles equal more depression. So the more particles, the lower the freezing point. Potassium nitrate is an electrolyte. It dissociates. It gives me I equal 2. So how many particles you're going to have? To get number of particles, let me erase this. To get number of particles, you need to multiply I times concentration. So that will be 2 times 0.2, that will be 0.4 molal of particles. Acetic acid is a weak electrolyte, and as you will see when I'm going to show you the lecture about electrolytes, non-electrolytes, weak electrolytes versus strong electrolytes, I for a weak electrolyte is slightly higher than 1. So number of particles in this case will be slightly higher than 0.2 molal. HCl have I equals 2. So the particles here is 2 times 0.1. So that's going to give me 0.2 molal of particles. And for sodium phosphate, which will dissociate into 4 particles, I equals 4. So total number of particles, 4 times 0.2 will be 0.8 molal of particles. So let's now circle number of particles for each one of them. For potassium nitrate, we have 0.4 molal. For acetic acid, we have slightly higher than 0.2 molal. For hydrochloric acid, we have 0.2 molal, and for sodium phosphate, we have 0.8 molal. The higher the number of particles, the more depression. So which one will have the lowest freezing point? It will be sodium phosphate will have the lowest freezing point, which will be followed by, I'm ordering them from the lowest freezing point to the highest freezing point, will be followed by potassium nitrate solution, followed by acetic acid solution, followed by hydrochloric acid solution. Okay? Now, if I am asking you which of the following will have the highest vapor pressure, well, remember the name of the vapor pressure depression. More particles, lower vapor pressure. So the higher vapor pressure will be, in this case, hydrochloric acid. The lowest vapor pressure will be sodium phosphate. If I'm asking about the boiling point, which one have the highest boiling point, the property name is boiling point elevation. More particles, more elevation. So the highest boiling point will be sodium phosphate. The lowest boiling point will be hydrochloric acid solution in this specific example. Okay? So that's it for this topic. Thank you very much, and I will see you in a next following lecture.